Okay, in this lecture we're going to talk about permutation symmetries. So we'll start by giving a motivation as to why this is an important topic, and then we'll go on to define what permutation symmetries are on sets, and then later in the context of graphs. And then we'll talk about how G and N sort of emerge from this framework once we define what our symmetry requirements are and have an approach for baking them in. So the motivation is that nodes in a graph do not have an inherent order to them. That's not part of the structure of the graph, is to have a notion of order. But whenever we put nodes in a matrix, like the adjacency matrix, we're effectively assigning an order to the nodes. And traditional machine learning models will depend on that ordering. So for example, if you train a classifier and you have a set of features like age and height, then if you start shuffling the column order around and put height where age is and age where height is, your model's going to break. But we want a model that gives the same answer regardless of the arbitrarily imposed ordering that we've assigned when representing these data structures. So to give a quick demonstration of this, you can imagine we have this graph here of these three nodes, x1, x2, and x3, and this choice of which one is 1, which one is 2, and which one is 3 is arbitrary. And I've just made one up here. And you can imagine that we have this matrix where there's some set of features for x1, which is just represented by this vector x1, and similarly for x2 and x3. And if we just had that, we'd be okay. But we have this adjacency matrix as well, because we want to use this graph information inside of our model. So we naively would just attach the adjacency matrix to the side here. And you can imagine we have some classification task and we fit the set of parameters theta for this neural network here, this MLP. However, if we were to order things slightly differently, if tomorrow we build the same model, but we call this one x1, and x2 up here and x3, it's okay for us to swap things around. However, you'll notice that the adjacency matrix doesn't look as if this information just got copy-pasted up to the next row and they were swapped. But the actual total structure of the adjacency matrix changed, and that's because for a single node, they are represented by both a row and a column in the adjacency matrix. So not just did our rows get shuffled up, but our columns did as well. And if we were to fit an MLP to this setup, we'd have a different set of parameters that would not match the first one. And if we plugged this data into this model, we wouldn't get sensical answers. So this is the essence of our problem here, where if our adjacency matrix will shuffle around both the rows and the columns if we start reordering things, and our models will break. So the idea we have here is that we want to build these fundamental symmetries into our model structure so that it can handle these cases elegantly and actually benefit from them. And we'll see how to do that in just a bit. But you could also imagine the brute force way, which is you just shuffle your graph representation, the ordering in your matrix, and you train a model on all the different ways you could do that permutation. But you can imagine, first of all, the number of permutations is enormous, and then you would be sort of wasting all this computation by trying to train the model to learn these symmetries. So another place where you see a model architecture leveraging the symmetry that it knows the problem has is in convolutional neural networks. So an image we know has this certain structure to it. And if you have, let's say, a face detector as one of these sophisticated filters, we know that if there's a face in one part of the image versus another part of the image, that it sort of means the same thing. And we wouldn't want to have to train a network that has to dedicate model capacity for finding a face in the upper left-hand corner versus the bottom right-hand corner. That would be a waste of parameters and we'd require much more training data. So the way that a convolutional neural network leverages this translational symmetry is they take a single filter and they scan it across the image. And it's this scanning property, which is what makes it convolutional in nature, that bakes in the translational symmetry into the model itself. So we want to do something similar, but with permutation symmetries. So to get started, we can see this permutation matrix where the indices here tell you how it will make the permutation on X. And the way you do this is you just put a 1. So this is 3, 1, 2. So we'll put a 1 in the third column for the first row, a 1 in the first column for the second row, and a 1 in the second column for the third row. And when you operate on a matrix of row vectors, you'll see that this matrix multiplication will pull the 3 up top, the 1 here, and the 2 here to match these indices. So now we can get to our definitions of our symmetries. So the permutation invariance means that if you shuffle the ordering of the inputs to this function f and get the exact same result, then f would be permutation invariant. So the act of shuffling had no impact on the answer, in other words. And permutation equivariance is slightly different. It means that if you shuffle the input, that's okay, but you'll have to shuffle the output in the exact same way for it to match. So in other words, it's maintaining the order that's given to it. So in the first case, the ordering information is just ignored. It has no influence on the result. And in the second case, the ordering information is maintained. So you can flip it before or after. So before digging deeper into these concepts, I want to have a kind of concrete example that we can keep referring to. So I just have this simple graph of 3 people, James, Mary, and Sally, and this kind of social connection where James is connected to these 2 people. And we'll say that each person has a vector of features. So maybe it's their age and height, as we previously used. So we just have a vector representing James, Sally, and Mary, where the index here is their name. And this also indicates the order here. So JSM means James is first, Sally's second, and Mary's third. So one way we can get permutation invariance is by doing an aggregation. So here again is our definition for invariance, meaning that the ordering information can be shuffled and it doesn't have an influence on the output. So we can achieve this by aggregating the arguments here. So an example would be a sum or an average or max or min. But using the sum for an example, if we add up all of the arguments here, it's not going to matter which order they're in. Likewise for max or min. So if you watch our lecture on the neural message passing framework, you'll recognize this notation here. So we basically have a collection of messages. So this is the neighborhood vector of I. It's operating on the collection of neighbors of node I, indexed here by j. And we have this collection of messages, and then we apply some aggregation function like sum. So this would sum up all of the messages coming from the neighbors of I. And this will be permutation invariant. So for example, if we have Sally, James, Mary, and we add up these features for each of these 3 in this order, we're going to get the same answer as if we fed in James, Mary, and Sally. So really we can treat this as a set, because a set doesn't have meaningful order. It's just a collection of things. So really we're just operating on this set that contains the nodes of James, Sally, and Mary. And one such example would be the sum. That's one type of aggregation function, so we could sum up the features from James, Sally, and Mary, and regardless of the order that we fed it into this sum, we would get the same answer, represented here by this m hat. In other words, we're able to achieve permutation invariance by aggregation. Now we move on to permutation equivariance, which we said means that you can permute the input, but you need to permute the output in the same way. Or in other words, it maintains the ordering information that you supplied to it. And one way to achieve permutation equivariance is by applying the same function to every node individually. So if we have some function phi, and we just apply it to the inputs x and get some new thing, which we're calling h here, and we just apply that recipe to every node separately, then we would have something that's permutation equivariant. So to give an example of that, here we have our permutation matrix being applied to x. So we're shuffling and putting x3 up top, and then x1, and then x2. And then we apply this function to each row individually. So we get phi of x3, phi of x1, phi of x2. And notice that that's the same thing as if we applied phi to x first, got phi 1, phi 2, phi 3, and then did the permutation to move things around. So regardless of the order of when we apply p, we get the same result, which is this thing in the middle. And to demonstrate this with our simple example, if we applied this permutation equivariant function to this ordering of our little graph, we would maybe get this thing out. Whereas if we shuffle around the inputs, we would get this other thing out where all of these things are the same in terms of value. It's just shuffled up in the same way that the input was shuffled. So really what this function is doing is it's mapping a list of inputs to a list of outputs, where the indexing of input to output is the same. So we have SJM, so we'll get SJM out the other side, but each one of these elements in the list will be transformed in some way. Okay, so why is this useful? We've defined what permutation invariance is. We've given an example, in this case aggregation. We defined equivariance and how we could do that by sort of applying the same function to everything individually. So the way this is useful is that a permutation invariant function essentially maps a set to a single output that doesn't depend on the ordering, and we can use this to get a representation of an entire node neighborhood, because a node neighborhood is essentially a set of nodes. So by using a permutation invariant function, we can find a representation for an entire node neighborhood. So here's this function f. The input to this function is a set. In this case, it's a set of vectors indexed by j, where j is all of the neighbors. And what we get out the other end is a single vector that's representative of this entire neighborhood. Permutation equivariant functions, on the other hand, allow us to get item level outputs for whatever ordering we supply to it. So, in other words, we can get a representation for every node in our graph, regardless of what ordering information we apply to it. It'll maintain that order. So here we have this function f that we're applying to every node, xi, and we're getting hi out the other side. So these will give us individual node embeddings, and this will give us neighborhood embeddings. And then we can stack these concepts together as well. So there's a pretty famous paper called Deep Sets, and in it they show that if you have a set with elements in it, and you apply a function, in this case an MLP, to every element in that set individually to transform it, you'll get a transformed version of that set. So that's blue box here. This recipe is equivariant. We're cycling through every element of the set and applying the same function to it. But then if you apply a permutation invariant function to that transformed collection, that's this green box here. So they're using a sum, but you could use any aggregator you wanted. And then map that through a different MLP. What you have is the deep set model. And they show that this is a universal set function approximator. So by following this recipe of equivariant plugged into permutation invariant that we can model any function on sets. So this gives us a recipe for building representations of graph neighborhoods. We can essentially use this deep set model. And that's essentially equivalent to what we've previously defined as the message and aggregation functions from the neural message passing lecture. So we have this message function that maps features to some vector, and then we have some aggregation function that collects all of those messages to have a representation of a node's neighborhood. Okay, so we've talked mainly about sets so far, but graphs are different because they not only have a set of nodes, but they have edges as well. And edges, as we know, can be represented as the adjacency matrix, but as we previously mentioned, if you permute the node ordering, then we need to permute the rows and the columns of the adjacency matrix. We now have these updated definitions of our permutation symmetries. So in the case of permutation invariance, we have the permutation matrix operating on X as we had before, but now we have it also operating on the adjacency matrix, both from the left side and the right side, to permute the rows and the columns. And for invariance, that would map to the same output as if you didn't do that. And then for equivariance, we have the ordering maintained so that if you do it to the input, you can also do it to the output. But there's a conceptual difference here as well. So before, we were applying the same function to every node separately in this permutation equivariant way. However, that doesn't use any information from the graph. That's just a function being applied to every individual node without any consideration for its neighbors. But we want our permutation equivariant function, which calculates our node embeddings, to operate not just on the node itself, but also on its neighborhood. And a neighborhood, as we mentioned, is a set of nodes. So whereas with sets, we had this recipe where our function phi operated on each element in our set, now with our graph, we want our function to operate on each node, but also on the neighborhood of that node. So whereas we have the features of node 1, we also have the set of neighbors of node 1. And then here we have the features of node 2 and the set of neighbors of node 2. So now here's our permutation equivariant function. Its inputs are not just the features, but also a set. So with our example here, our first row is for James, but the other argument to this function is the set of neighbors, which is Mary and Sally. Then this next row will represent the embedding for Mary, but her neighborhood will include James, and similarly for Sally. But of course, we won't have circles, we'll have vectors that represent, the features of these various things. And this is where graph neural networks emerge from this idea. So GNNs will give us node-level outputs that also take neighborhoods into account, but they do not depend on our arbitrary ordering. So in other words, we have a permutation equivariant function f that operates on our node features and our graph structure. And we achieve this equivariance by applying this function to each node and its neighborhood independently. So we apply this one function to the first node in its neighborhood, the second node in its neighborhood, and so on. They share parameters, in other words. And to maintain equivariance for this overall function, we have this neighborhood function needs to be permutation invariant because the argument to it is a set. And we already said that the way we get permutation invariance is we do aggregation. So the recipe for graph neural networks is, yes, you pass in the node features and its neighbors, but you specifically need to apply a permutation invariant operation to this set of neighbors, which is an aggregation, represented here by this O plus sign. So this could be a sum, a max or min, or so on. So in other words, we get this permutation equivariant function out, which gives us our individual node embeddings. But the way we get that is we apply a permutation invariant function to this set of features here. If this were not permutation invariant, then it would depend on ordering, because we would get different outputs depending on the order we fed into it. And that would not have this permutation equivariant property. So now, whereas before we just were showing what the input was, which is this set, now we see that we're applying a specific operation to this set, which is some aggregation function. And this is, in essence, the recipe for graph neural networks. So to put all of this simply and kind of take a step back, we want a model that doesn't care about the arbitrarily imposed ordering that we've applied, but we do care about maintaining the ordering because we want to be able to make node-level representations and predictions. So we couldn't have a recipe that shuffled everything up, because then we wouldn't be able to figure out which representation matches which node. So we need to maintain the ordering that we've applied. So the recipe we've developed for satisfying this criteria is that we get node-level outputs that respect node ordering, which is permutation equivariant, and we get that by applying a function to each node neighborhood that's robust to the node ordering itself, so the permutation invariant piece. So that's the part that is not sensitive to ordering. So we kind of get both by doing something for each neighborhood that's not sensitive, but by doing it in a way that maintains the ordering we have imposed, we get the best of both worlds. So the outcome is we have a model design that has these permutation symmetries built into it. So in the same way that convolutional neural nets have come up with this scheme for building translational symmetry into them by this recipe of scanning a filter across image patches, we have graph neural networks that take advantage of permutation symmetries by mapping these permutation invariant functions to each node neighborhood individually. Sort of like scanning across the image, but we're scanning through every node neighborhood in the graph and applying something that's permutation invariant so that we get our node and neighborhood level representations in a way that's not sensitive to the ordering we applied. So if you'd like to dig deeper into this topic, I wanted to point you to some people that are kind of leading the charge in this framework. So Michael Bronstein, Joan Bruna, Peter Velikovich, and Taco Cohen have been working together on this book called Geometric Deep Learning, Grids, Groups, Graphs, Geodesics, and Gauges. So this is a kind of unifying book that talks about these symmetry first principles and shows how lots of other things fall out of it, graph neural networks being one of them. But these this geometric deep learning is exploring more than just graphs here, and they're making these connections across many different things. So this is definitely worth checking out. Peter has given some talks on this topic recently that's very interesting and helped motivate some of this material. So the talks are listed here, the slide and the YouTube video. And then Taco Cohen has a PhD thesis that's all about building symmetries like this and others into models. So, for example, rotational symmetries, and they go beyond just permutation symmetries. And his PhD thesis is freely available and linked here. It's called Equivariant Convolutional Networks. So check that out. That's it. I hope you can see how the recipe of graph neural networks emerges once we state what our symmetry requirements are and work backwards from there.